Okay. So there's a lecture on the fundamental theorem of calculus on YouTube, of course. And I'll review it a little bit. But are there any questions before I start? So I guess it's called the fundamental theorem because it's so fundamental. And it connects the derivative and the integral. So FTC, fundamental theorem of calculus. So you have a function f of x continuous on the closed interval from a to b with an antiderivative, capital F of x. Then the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. So for example, a, b, and here you have the function y equals f of x, and you want to find the area under the curve. That's what the integral, the definite integral tells you. You find the antiderivative, and it's the difference of the antiderivative evaluated at the endpoints. And a rough sketch of the proof would go like this. Here's the interval from a to b, x0, x1. Partition this up into n pieces. So here's the nth piece. And by the mean value theorem, if you just look at the difference of the antiderivative x, f of xi minus f of x sub I minus 1, this is equal to f prime of some x, there's some c sub I in this interval, times xi minus 1. That's the fundamental theorem of calculus, but capital F is the antiderivative, so this is equal to little f at c sub I, xi minus 1. So that says that the area of this rectangle from xi minus 1 to xi, that's the base times the height, f of ci. It's just the difference of the antiderivative evaluated at the endpoints. And so f of b minus f of a, this is the sum of f of xi minus f of xi minus 1. This is a telescoping sum. I goes from 1 to n. Everything on the inside cancels. Summation I goes from 1 to n. F of c sub I, I'll just call this delta x sub I. And this approaches, this is the Riemann sum. Excuse me. Resume. Sorry. Yeah. So this is just the Riemann sum. And this is essentially the proof that the definite integral from a to b is the difference of the antiderivative evaluated at the endpoint. And there are lots of important examples of this. Suppose we want to find the integral from 1 to 2 of x squared minus 3 dx. So this is a definite integral. What does the graph of that look like? This is the parabola x squared shifted down by 3. So when x is 0, it's minus 3. When x is 1, it's minus 2. When x is 2, it's plus 1. When x is minus 1, it's also minus 2. This is the parabola. It looks like this. And from 1 to 2, the integral is the area above the x-axis minus the area below the x-axis. This minus this. So in order to evaluate this, this is capital F of 2 minus capital F of 1, where capital F of x is the antiderivative of x squared minus 3, which we know is a third x cubed minus 3x. So this is equal to, what is F of 2? A third 2 cubed minus 3 times 2. That's 8 thirds minus 6. That's minus 10 thirds. And F of 1 is 1 third minus 3, which is minus 8 thirds. So what we get is minus 10 thirds, F of 2, minus 8 thirds is minus 2 thirds. So the area above the x-axis minus the area below is a negative 2 thirds. That's the fundamental theorem of calculus. Suppose we take the integral from 1 to 4 of 3 times the square root of x dx. So this is the square root function, 3 times root x. When x is 1, this is 3. When x is 4, it's 6. We want that area. So the antiderivative of 3 root x dx, that's 3 times the integral of x to the 1/2 dx. When you add 1 to a half, you get 3 halves. So you get 3 over 3 halves, x to the 3 halves, which is 2x to the 3 halves. That's the antiderivative. So we get f of 4 minus f of 1. That's 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. 16 minus 2 is 14. That's the area under the curve. Any questions about this? This is bread and butter calculus. This is what you have to know on the final, for example. Look at another example. The integral from 0 to pi over 4 of secant squared x dx. Well, you have to remember the derivative of the tangent is the secant squared. So the antiderivative of the secant squared is the tangent. So this is f of pi over 4 minus f of 0. That's tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1. Tangent of 0 is 0. So the answer is 1. Any questions about this? Suppose we had the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Now here, you're not going to be able to find the antiderivative very easily because of the absolute value signs. But let's graph this and see what the graph of this looks like. The integral from 0 to 2. Actually, let's make that 2, this 1. This is a half, and this is 3/2. So what can we say about the absolute value? The absolute value of 2x minus 1 is 2x minus 1 if 2x minus 1 is greater than or equal to 0, which is the same as x greater than or equal to a half. So for x greater than or equal to a half, this is just 2x minus 1. That's the line with slope 1 and y-intercept minus 1. So when x is a half, this is 0. And when x is 2, this is 3. Just that line. And the absolute value of 2x minus 1 is minus 2x minus 1. If 1 minus 2x is greater than or equal to 0, or x is less than or equal to a half. So this is 1 minus 2x. So this is what the graph of this absolute value function looks like. They're really two separate pieces. So I can write this as the integral from 0 to a half of 1 minus 2x dx plus the integral from a half to 2 of 2x minus 1 dx. And I can evaluate each of these separately because I can find the antiderivative of each of them separately. The antiderivative of 1 minus 2x is x minus x squared. The antiderivative of 2x minus 1 is x squared minus x. So my integral this is, let me call this function capital F of x, and I'll call this capital G of x. So this is the antiderivative evaluated at a half minus the antiderivative evaluated at 0. And for this, the antiderivative is x squared minus 1, g of 2 minus g of a half. So f of a half is a half minus a fourth, and f of 0 is 0. And g of 2 is 4 minus 2, and g of a half is a fourth minus a half minus a fourth. So this is 2 plus a fourth minus a fourth plus a half. It's 2.5. 5 halves. All right, any questions about this? There's also a nice mean value theorem for integrals. We saw already today the mean value theorem for derivatives. So the mean value theorem for integrals says the following. Suppose from a to b, you have a function f of x, and suppose that m is less than or equal to f of x is less than or equal to capital M for x between a and b. So this function is always greater than or equal to little m and less than or equal to capital M. So the area in this curve, the integral from a to b of f of x dx, is less than the area of this rectangle, the height times the base, and greater than or equal to this rectangle, whose area is the height times the base. So you get that 1 over b minus a, the integral from a to b of f of x dx, is some number between the minimum and the maximum value of the function. And if f of x is continuous on the interval from a to b, then it takes every value from little m to big M. So this is going to be equal to f of c. So if f of x is continuous, it means there exists some c between a and b such that this holds, or f of c times b minus a is the integral from a to b of f of x dx. So this is often very useful. It's the mean value theorem for integrals. And we also use this to define the average. So the average value of a function f of x on the interval from a to b is defined to be exactly this. You take divide by the length of the interval, and times the integral of the function over the interval. Now, there's another version of the fundamental theorem of calculus, which is very nice. And it's based on the following idea. Suppose you have a function y equals f of x. And it's defined and continuous on an open interval containing a, so your function, some continuous function. And if you fix a number x in the interval, you can calculate the integral from a to x of f of t dt. So that's some function I'll call capital F of x. So you fix the lower limit of integration. As x varies, this area gets larger or smaller. It varies as well. And if we take the derivative of f prime of x, what is this? This is the limit delta x goes to 0, f of x plus delta x minus f of x over delta x. What does this correspond to? F of x plus delta x, here's some x plus delta x. That's the area under the curve from a to x plus delta x. F of x is the area under the curve from a to x. So what this is, it's the area in this strip. So this is the limit as delta x goes to 0, 1 over delta x, the integral of the function f of t dt from x to x plus delta x. But now we can use the mean value theorem. This is equal to one over delta x. This is f of c times the length of the interval delta x for some c between x plus delta x. And these delta x's cancel. So this is the limit as delta x goes to 0 of f of c. C is some point squeezed between x plus delta x and x. When delta x goes to 0, c approaches x. This is just f of x. So what this tells us is if we define the function capital F like this, the integral from a to x of f of t dt, if I differentiate that with respect to x, I get f of x. So if I take a function, I integrate it, and then I differentiate it, it gives me back the function. And this function capital F of x is an antiderivative of f of x. So that's a very nice geometrical argument. And let's just look at a couple of examples of this. Again, please interrupt if you have any questions because it's a very quiet group. Suppose we have the integral from 0 to x of the square root of t squared plus 1 dt. So that's some complicated function of x. But if I differentiate it, I get what's under the integral sign evaluated at x. And when it's a little bit more complicated, you use the chain rule. So suppose we let capital F of x be the integral from pi over 2 to x cubed of cosine t dt. So we want to find f prime of x. And this is a kind of a composite function. If we were to let, for example, g of u be the integral from pi over 2 to u cosine t dt, then f of x is g of x cubed. So f prime of x would be g prime of u du dx, dg du dx. The derivative of this with respect to u is cosine of u, and u is x cubed, du dx is 3x squared. So we get 3x squared cosine of x cubed. Any questions about this? Let's look at a couple more examples. These are sort of applications of what we've just been doing. So the fundamental theorem of calculus says the integral from a to b of f of x dx is capital F of b minus capital F of a, where this function capital F is the antiderivative of x, right? F prime of x is little f of x. So another way of saying this is the integral from a to b of capital F prime of x dx. That is, I take the function capital F, I differentiate it, and then I integrate it, and this is equal to f of b minus f of a. So what this is, what you might call is the net change of the function capital F of x on the interval from a to b. That is, how does the function capital F change? It starts at the value f of a, it ends with the value capital F of a, it ends with the value capital F of b. The net change is this difference. That's how much capital F changes over the interval. And that's exactly what you get by integrating the derivative from a to b. So here's an example. This is in the book. This is example 9. We have a storage tank and a chemical is flowing in. At a rate of 180 plus 3t liters per minute. So the rate at which the chemical is flowing into the tank is faster and faster, and at time t, the rate is 180 plus 3t. Find the rate at which the amount of chemical that flows in, find the amount of chemical that flows into the tank in the first 20 minutes. So suppose we let C of t be the equal to the amount of chemical in the tank at time t. And we want to figure out how much chemical has gone into the tank in the first 20 minutes. How much additional chemical? What's the increase? What's the net change? So what we want is C of 20 minus C of 0. Right? That's the net change over 20 minutes. And by the fundamental theorem of calculus, this is the integral from 0 to 20 of C prime of t dt. And C prime of t, this is the rate at which the chemical is flowing into the tank. This is the integral from 0 to 20 of 180 plus 3t dt. The antiderivative of this is 180 t plus 3/2 t squared. And we want that evaluated from 0 to 20. At 0 is 0, and at 20, this is 180 times 20 plus 3/2 times 20 squared. This is 3,600 plus 400 over 2 is 200 plus 600 is 4,200. So the net change in the tank over 20 minutes is 4,200 liters. Any questions about any of this? So if you're learning this for the first time, there really is.
Will this be also in the final?
Yes. Yes. I mean, you already have, I posted on Blackboard at the beginning of the semester, a practice final. It's like the review for the final. I'm going to go over it on Monday. But the final is made by the department, and it's comprehensive. It covers everything in the syllabus, including integration. I don't make up the final, I just give it, but that's what it is. Let's look at another problem or two. So imagine we have the situation of a particle moving along a line. So we have a particle moving, and S of t is the position of the particle at time t. So over a time interval from t equal a to t equal b, the net change in position, S of b minus S of a, is the integral from a to b of S prime of t dt. But of course, the derivative of the position is just another name for the velocity. So if you integrate the velocity from a to b, you get the net change in position, or the displacement. So suppose a particle, so this is an example. This is example 10 in the text. Particle moves with velocity at time t, v of t equal to, a little bit complicated, t cubed minus 10t squared plus 29t minus 20. Find its displacement, the net change in position from t equal 1 to t equal 5. So the displacement, the net change in position, is the integral of the velocity. So the displacement, the difference between its position at time 5 and its position at time 1, is the integral from 1 to 5 of the velocity. That's the integral from 1 to 5 of this function t cubed minus 10t squared plus 29t minus 20 dt. When you integrate this, the antiderivative is a fourth t to the fourth minus 10/3 t cubed plus 29 over 2t minus 2t squared, 29 over t squared, minus 20t, evaluated from 1 to 5. And when you do this calculation, you get 32 over 3. That is, you literally have to take out a big piece of paper or a calculator and just do this calculation. Everything's over a denominator of 12, and then there's some cancellation. And it gets 32 over 3. So now this is the net displacement. So you can imagine a situation like this. Suppose you end your start here on the line, and that's where you are at t equal 1. And then you move over and you move back and you move over and you move back and you move over and you end up over here. So you've done a lot of traveling But the total displacement, the net displacement, is just this. It's the difference from where you ended up and where you started. But it's not how much ground you covered when you were traveling, because when you were traveling, you had this amount plus this amount plus this amount plus this amount plus this amount. And there was a lot of cancellation. The net displacement was this. But suppose you want to know like the absolute amount, the total distance you actually traveled. How do you figure that out? It would be this. You have to add up all these pieces. So let's try and figure out total displacement. As opposed to net displacement, or the total distance traveled. Again, if you go from 0 to 1 and back to 0, your net displacement is 0. You started at 0 and ended at 0. But your total displacement is 1 to the right plus 1 to the left is 2. And this total displacement, or the total distance traveled, you will get this by integrating from A to B of the absolute value of your velocity. When you're moving to the right, the velocity is positive. When you're moving to the left, the velocity is negative. But if you take the absolute value, it's always positive, and you get the total distance traveled. So in the problem we just considered, the velocity was t cubed minus 10t squared plus 29t minus 20. For t from 1 to 5. And we want to integrate the absolute value of this. So for that, we need to know when is this positive and when is this negative. So if you look at this, what can we do? It turns out this factors, and first t minus 1 divides into this. You divide t, because if you put in t equal 1, you get 0. So t minus 1 divided into t cubed minus 10t squared plus 29t minus 20. This goes in t squared times. I get t cubed minus t squared. So this is minus 9t squared plus 29t. So this is minus 9t. So I get minus 9t squared plus 9t. When I subtract, I get 20t, bring down the minus 20. This goes in 20 times. I get 20t minus 20. So this is equal to t minus 1 times t squared minus 9t plus 20. And this factors into t minus 1, t minus 4, t minus 5. So this function is 0 at 1, 4, and 5. And between 1 and 4, so when t is bigger than 1 and less than 4 and less than 5, this is positive, negative, and negative. Here, v of t is greater than 0. But when t is bigger than 4, these are both positive, but this is negative. Here, v of t is less than 0. So if I want to integrate from 1 to 5, the absolute value of v of t, this is the integral from 1 to 4 of v of t. Because it's positive there. And from 4 to 5, it's negative. So I want to integrate minus that. So it's minus the integral of t cubed minus 10t squared plus 29t minus 20. And if I do the integral, the calculation you can do yourself, or you can look at the text, you get 71/6. So this is the total displacement as opposed to the net displacement, which was smaller. Okay. All right, so I actually just covered everything in this section, though you'll find this in the lecture. And the real purpose of these sessions is to go over homework problems and answer questions. Are there any questions or problems you would like me to do from this or previous homeworks? It's important not to fall behind at the very end, because there are always several questions about integration on the departmental final. And I always put extra points on an exam, but in the departmental final, there are no extra points. It's graded, there are 100 points, and it's just graded on the basis of 100. You get what you get. No? All right, well, maybe I'll pick 1 or 2 problems from the homework just to have some fun. So, for example, number 27. The integral from 0 to pi of 1 plus sine x dx. So you have to find the antiderivative, capital F of x, the antiderivative of 1 plus sine x. What's the antiderivative of 1? What is a function whose derivative is 1? Can anyone tell me? It's x. What's a function whose derivative is sine x? Minus cosine x. So this is the antiderivative. So you evaluate this at pi minus this evaluated at 0. So that's pi minus cosine pi minus 0 minus cosine 0. Pi, cosine of pi is minus 1. So it's minus minus 1. Minus 0 plus cosine of 0 plus 1. So this is pi plus 2. That's the integral. Number 45, find the area of the region bounded by the graphs of the equations y equal 1 plus the cube root of x, x equals 0, x equal 8, y equals 0. So from 0 to 8, this is x equals 0, this is x equal 8, this is y equals 0, and 1 plus the cube root of x, when x is 0, this is 1. When x is 8, cube root of 8 is 2, 1 plus 2 is 3. So we want to find the area under this curve. So the area is the integral from 0 to 8 of 1 plus the cube root of x dx. What's the antiderivative? The antiderivative of 1 plus cube root of x. Cube root of x is x to the 1/3 dx. This is x plus 3/4 x to the 4/3. Right? So this you need to know by now. This is, so we're evaluating, so this is my function capital F of x. F of 0 is 0, so this is just f of 8. So that's 8 plus 3/4, 8 to the 4/3. 8 to the 1/3 is 2, 2 to the 4th is 16. 16 over 4 is 4. This is 8 plus 3 times 4. 8 plus 12 is 20. That's how you do the problem. Any questions about this? Let's look at number 87. In the homework, number 87. So capital F of x is the integral from 8 to x of cube root of t dt. So the antiderivative of the cube root of t, that's the antiderivative of t to the 1/3. So you add 1 to 1/3, you get 4/3, 1 over 4/3, t to the 4/3, or 3/4 t to the 4/3. So this is my so when you evaluate this at x, you get 3/4 x to the 4/3. When you evaluate this at 8, you get 3/4 8 to the 4/3. 8 to the 1/3 is 2. We saw this a moment ago. 2 to the 4th is 16. 16 over 4 is 4. This is 3/4 x to the 4/3 minus 12. And if you differentiate this, f prime of x, that's the derivative of 3/4 x to the 4/3 minus 12. This is 3/4 times 4/3 x to the 1/3 minus 0. These cancel. You get x to the 1/3, or the cube root of x. So what we've just demonstrated, again, is an example of the second fundamental theorem of calculus. The derivative with respect to x of this integral from 8 to x, cube root of t dt, is the cube root of x. We'll do one more that involves total distance traveled. So this is the last problem in the homework set, number 113. The particle is moving along the x-axis. The position of the particle at time t, x of t, is t cubed minus 6t squared plus 9t minus 2. for 0 between t and 5. Find the total distance traveled. So the total distance traveled is the integral from 0 to 5 of, you take the velocity v of t, its absolute value dt. Now, what is the velocity? The velocity is the derivative of the position. So the derivative of the position is 3t squared minus 12t plus 9. So if I factor out a 3, that's t squared minus 4t plus 3. And I should be able to recognize this factors into 3 times t minus 1, t minus 3. So I'm only interested in the interval from 0 to 5. When t is between 3 and 5, the velocity is positive. When t is between 1 and 3, this is positive and this is negative. The velocity is negative. When t is less than 1, these are both negative and the product of two negatives is positive. So for the velocity is positive. So the total distance, let me just call this t for short. T is the integral from 0 to 1. Yeah, this is positive, so the absolute value of the velocity is just the velocity. From 1 to 3, the velocity is negative, so it's minus the integral of the velocity. And from 3 to 5, it's positive again. So for this problem, the hard thing is to set it up. This is what we're integrating, and we know the antiderivative, right? The antiderivative of 3t squared minus 12t plus 9, when you integrate, you get t cubed minus 6t squared plus 9t. Basically the position. So, which is basically x of t plus 2. So this is going to be x of 1 minus x of 0 minus x of 3 minus x of 1 plus x of 5 minus x of 3. And this is just a calculation you do and you get the answer. But for us at this point, the hard thing is to set the problem up and to understand how to calculate a total distance traveled. Any questions about this? Let me remind you that the final exam is next week on Wednesday. So it's a week from Wednesday from 11 to 1. And the final exam is just like the practice exam. So you really should spend some time looking at the practice exam. There's one more lesson to cover where we learn one technique for doing integrals, that what is called substitution. And we'll do that on Wednesday. So Wednesday, substitution. Next Monday, review. Next Wednesday, final exam. Okay. Any questions before we quit for the morning? I mean, I can stay as long as there are questions, but when there are no questions, we're done. No? Okay.
Excuse me, Professor.
Yes.
When is late work last due?
Basically up until the final exam day. Of course, I try to exam.
Okay, yes.
As soon as I grade the final exam, I record the grades. I send the grades to the registrar. So up until the final exam. late homework is, whenever I get it, I grade it, but once I turn in the final grade, I can't, that's it.
Okay, thank you.
Sure.
Have a good one.
Okay. All right. See you on Wednesday. Bye all.